Now we are going to discuss the PDV work. We have seen different types of work, out of which displacement work is one type. We have seen electrical work, displacement work, shaft work, spring work, etc. So this displacement work is of different types. That is the PDV work. Okay. So we have already seen you can use the expression PDV, integral PDV, only for a quasi-static process, and we know what is a quasi-static process, that is a near equilibrium process. So mainly we deal with these kind of processes in thermodynamics, that is constant pressure process, that is pressure remains constant throughout. This is also called isobaric process. Then you have the constant volume process or isochoric process. Okay, this is the another type of process in which volume is constant throughout the process. Then you have the constant temperature process or isothermal process where temperature is constant. Then you have the adiabatic process in which there is no exchange of heat with the surroundings. Okay, so there is Q will be 0. And then you have the polytropic process. We will see what it is in later. So first let us discuss constant pressure process or isobaric process. So isobaric process can be shown in a PV diagram. In a PV diagram from state 1 to 2. So initially state of the system is 1. Now it undergoes a process and reaches 2. Okay. So what is the work done in this process? So work done can be calculated. We have seen uh, the formula, that is the PDV work. If this process is quasi-static, then you can use this expression to calculate the work done. So since pressure is equal to constant, you can write W12 as P into V2 minus V1. That is pressure into, because pressure is constant, so pressure into the final volume minus initial volume. And see, uh, we assume this gas to be ideal. So for you can abuse the ideal gas equation here, that is PV is equal to MRT. So if you make use of this equation, then you can write W12. See, you know that Q is equal to delta U plus W. That means when you supply heat, part of it will be used to raise the internal energy and part of it will be used to do work. So delta U, we have already seen the value expression for delta U or change in internal energy is mCV T2 minus T1. So Q can be found using this expression, that is mCV T2 minus T1 plus P into V2 minus V1. Okay. So and P into V2 minus V1, actually this can be written as MR into T2 minus 1 because this is an ideal gas. So P into V2 minus V1 can be written as MR into T2 minus T1. So so work can be, so this is the expression for work. You can also this expression for calculating work. So Q will become is equal to mCV T2 minus T1 plus MR T2 minus T1. Okay, so this can be written as M into CV plus R into T2 minus T1, which is equal to, so Q is equal to mCp T2 minus 1. So this is the expression for the heat or the heat added or rejected in the process in a constant pressure process. So Q is equal to mCv T2 minus T1 and delta U is equal to mCv T2 minus T1 and W12, the work is equal to P into V2 minus V1, or you can use this expression MR T2 minus T1. So these are the important expressions you need to keep in mind for a constant pressure process, or you can call this isobaric process.